Chapter 16. Chapter 16 is about our marine resources. The central case is about marine reserves, which are protecting certain areas from fishing and from harvesting. And we'll talk a little bit more about marine reserves at the end of the chapter. All right, so turn the page to 468. And 468 talks a little bit about the breakup of the ocean's water in terms of its salinity. So what you need to know on this page is that the ocean water is about 3.5% salt, which we call 35 parts per thousand. I know we've used PPT as parts per trillion before, but in this case it actually stands for 1,000. On average, some places have a little bit more salt and some places have a little less. So it could range anywhere between 31 parts per thousand or even 38 parts per thousand. But average, it's 35 parts per thousand, which is, again, 3.5%. Salt is low near the equator due to a lot more rain. Actually, at the equator. Just below and above the equator, you're going to get less rain and a lot of evaporation, so it's actually saltier there. But again, low salt near the equator due to precipitation. Saltiness is high between 30 and 35 north and south latitude due to evaporation. We are located at about 34 north latitude on the globe, and so the salt in our oceans is going to be saltier than the average. On the next page, make sure you know the pictures and the caption, which talks about something called thermocline and pycnocline. And the caption here explains it very well. And make sure, again, you know that the thermocline is a zone of rapidly decreasing temperature with depth, and the pycnocline is rapidly increasing density with depth. Because when water gets colder, so decreasing temperature is colder, it also gets denser. So decreasing temperature equals increasing density, because, again, colder water is more dense. So this thermocline up here shows the drop in temperature, and the same with density here. There's one region in the world that does not have a thermocline or pycnocline, and that would be the polar region. It's cold at the top, it's cold at the bottom. So the polar region really does not have a thermocline. The most dramatic thermocline is your tropical area. The temperature's got to drop a lot. Once you're at about 1,000 meters in depth, no matter where you are in the world, it's about the same temperature. Turn to page 470. You need to know about the Gulf Stream. You don't need to know about that. The Gulf Stream is the current in the Atlantic. It's right here on the map, and it brings warm water up from the equator to northern Europe. And it's the only reason here why people can actually live in England and Ireland and also Sweden, Finland, Norway. Otherwise, it would be too cold. This water, again, is warm. It comes up here and it makes it habitable. You can grow crops in the summer and you can live there. Otherwise, it would be too cold. Because, again, the ocean water influences climate. So when you have warmer ocean water, you're going to have a warmer climate. Water in general has high heat capacity, and if you remember from chemistry, this means that it takes a lot of energy to change the temperature, either lower or higher. This means that water can absorb a lot of heat during the day, during the sunshiny day, and release it at night. So what happens is that if you live on the coast, Ventura, Malibu, Santa Monica, you're going to have a milder climate. It's going to be warmer during the winter and cooler during the summer because the water will moderate the temperature because of its high heat capacity. The next page on 471 shows upwelling. The picture explains it really well, and upwelling is really important. What happens is that the winds blow from north to south along the California coast. The spinning of the earth diverts the surface water off to the side. The spinning of the earth And the diversion of not just water but also wind is called the Coriolis Effect. Now the water is being blown this way, and so water from below comes up to replace it, and that is called upwelling. So cold, nutrient-rich water comes to the surface and begins the food chain. This is why most life in the ocean is near the coasts, because of upwelling. And also near the surface because of photosynthesis. Your base of your food chain are your phytoplankton, and they need sun. So even though there's a lot of nutrients down here, there's no sun. So when the nutrients from here get to the top, to the sun, you're going to have the start of your food chain. Another thing, well, where do these nutrients come from? Well, on the bottom of the oceans, there's nutrients because of dead, decomposing fish and whales or whatever. So whatever dies in the ocean sinks to the bottom and decomposes. So you have a lot of nutrients. Also, rivers and streams bring nutrients from land into the ocean, and the nutrients from land kind of sink down in here into the ocean as well. That's also another reason why most life in the ocean is near the coast. Not just upwelling, but because rivers and streams bring nutrients from land into the ocean as well. Your open ocean is actually sometimes called a desert because there's not a lot of life there. Downwelling is the opposite of upwelling. Very little life due to no nutrients for your plankton to start the food chain. Page 472 shows some of the layers of the ocean. The layers that you need to know for your next test is on 473, the photic zone where there's light, the intertidal zone where you have your tide pools, the pelagic zone is kind of the open ocean where you just swim around, and benthic zone is anything that's on the bottom. Even near the coast, as long as it's on the bottom, it's called benthic, all the way down to the deep sea. Turn to 474. 474 talks about kelp forest. Here's a picture here of kelp forest. That's my little reminder for a video there, so you can ignore that. Kelp forest is a coastal ecosystem off the coast of California. It's very unique. It's only found here, and it's in cold, temperate waters. Temperate is halfway between the equator and the poles. So around the equator we call it tropical zones, and then around the poles we call it the polar zones, and then in between it's the temperate zones. All right, talking about coral reefs. Corals are mutualistic. That's a little U right here. Mutualistic with something called zooxanthellae. The X has a Z sound, which is an algae. And the corals and the zooxanthellae live together and have to live together. The zooxanthellae is sensitive to temperature and to pollution and can leave the coral if the temperature gets too hot or pollution is too bad. When the zooxanthellae leaves the coral, it's called coral bleaching because the zooxanthellae provide color for the coral, and when the zooxanthellae leave, there's no color, and so the corals look white or whitish. Other threats to coral reefs: fishing techniques can harm the corals. The corals are cut for ships to go through, and sewage and toxins hurt the reefs. Benefits of corals: biodiversity is a positive. Coral reefs absorb wave energy, so that's an economic benefit. That's why the dollar sign's there. So the waves don't crash into land so violently. They're also a nursery for fishes, which provides income for fishermen. The fish grow and are protected in the coral reefs, and they swim away, and then the fishermen can catch them. Coral reefs provide tourism with snorkeling, scuba diving, and that's an economic benefit. And coral reefs are found in tropical waters mostly. There's actually some cold corals they've just discovered way deep down in the Atlantic Ocean. But in essence, what you really need to know is that corals are tropical, warm water areas. Turn to page 476. We have another zone, which is the Intertidal Zone. And this is a harsh environment with large extremes in temperature, moisture, sun, salinity, air. And so if you live in the tide pools, starfish and sea anemones and crabs and clams, mussels, barnacles, you've got to have very good adaptations to be able to survive in all of these kinds of extreme environments. The next page, we talk about salt marshes and mangrove forests. We studied those a little bit. Last chapter we did the big bubble map, sticky note, about salt marshes and mangrove forests, so refer back to that when you are studying. An estuary is anywhere where a river meets the ocean, so salt marshes and mangrove forests are both estuaries. Estuaries have brackish water, which is part fresh and part water. Okay, so the river meets the ocean, and when the tides come in, all that water from the ocean and water from the river gets mixed together, and so you have part salt and part fresh. The picture up here shows the mangrove forest, shows the roots that go deep underwater in the mangrove forest. Page 479 talks about ocean mining. We mine for sand, gravel, sulfur, salt, calcium carbonate, silica, and something called manganese nodules, which is magnesium, are abundant in the ocean and probably profitable too. We think that they will be extremely profitable in the future. We have a lot of ocean drilling in the Gulf of Mexico for oil, and also off the California coast we have a lot of drilling for oil as well. That's not necessarily mining, but we do ocean drilling there. Also, you need to know about methane hydrate, which is a potential fossil fuel energy source. We need a lot more research into this to see if we can use it as a fuel source, but as of right now, we think it is a good alternative to, it's a type of natural gas, and we think it might be okay, but it might be a little dangerous to get out of the ocean as well.